nanohub.org.
Online simulation and more for nanotechnology.
Hello and welcome. This is the third recitation in a series for semiconductor device education. And today I'll like to talk a little bit about band structure and band models and how to use some of the tools in the classroom. Just for intro, again, I'm going to start from the homepage at NanoHub. There's really four major agenda items, so to speak, that we have in mind with NanoHub. We want to enable people to model and simulate nanoscale phenomena. So we have over actually 700 apps now in NanoHub that enable that. We want to help people learn and teach with these tools, and I'll focus on this here. But we also want to enable people to develop software such that they can deploy it on NanoHub. So that's the third item here. And ultimately to enable people to share and publish their results and make them duplicatable and have impact on the community. So on the learning and teaching part, there's a variety of resources. Today I want to focus on the simulation-powered curriculum. So teaching materials that are based on modeling and simulation. And if you click on this link from the front page, you'll see an overview of the various tool sets we have. And there's a couple of them that deal with quantum mechanics and computational nanoscience, computational electronics, general chemistry. And I want to focus on semiconductors. That's my prime topic that I'm actually using and teaching as well in my class, and I help to develop this. So if you click on this, you'll go to this assembly of basic applications for coordinated understanding of semiconductors. You have to come up with a cool acronym, right? So that's ABACUS. And what is it about? So with ABACUS, you can teach a standard semiconductor course. You'll probably start with crystals and lattices. You'll introduce band structure and band models, maybe bulk semiconductors. Then you go to p-n junctions. Some people include the BJT, and then you typically go to MOSFET and MOS capacitors and MOSFET. So today I want to talk about band structures and band models, and I'll show two different tools. One dealing with the traditional periodic potentials, or the Kronig-Penney model, and I'll start from there. And the other one, which I actually like better, because it's more relevant to nanoscale devices where you can see really band structure emerge. But so if you click on any of these tools, what happens is you go to the actual tool. And I guess I didn't make the point here. Let me do that. So this group page about ABACUS is really a wiki that is full of information in terms of additional resources, animations, some homework assignments, etc., that allow you to hopefully integrate these tools into your classroom. So let me go into this tab here. Ooh. Oh, there we go. So you get to this ABACUS tool once you click on any of these animations, and it's a proper publication on NanoHub. It's actually now also listed in the Web of Science. It has a DOI. So in a sense, we created new publications, if you will. The latest version was published recently, but it's been up and running for quite a while. We had over 16,000 users that utilized this tool set. And there's a couple of screenshots to highlight some of the features. There's a question and answer forum. There's some reviews. You can put in wishes of how to improve the tool or new features you would like. And if you click on Launch Tool, you'd be either prompted to log in for a free login. And since I'm logged in already, I can just push this launch. And like in any cooking show, as this tool launches here, I already had one pre-cooked, but these tools launch pretty fast. So here is ABACUS. It's really this assembly of different tools. So any of these tools you can also find on NanoHub independently, and finding them is a bit of a challenge. And really, we wanted to make a one-stop shop for faculty members to find the material they need for this type of specific course. So again, you might start from crystals and then go into periodic potentials or band structure formation. I have a tool in here that looks at bulk band structures and also nanowire band structure. Then Fermi distributions, drift diffusion lab to look at bulk semiconductors. Then there's p-n junction lab that I talked about last week. And then here, MOS capacitor and MOSFET. Here on the bottom, we have older versions, or let's say versions that are fuller equipped, if you will. In this table, I'm going to try to demo most of it, this newer version here of the periodic potential lab. So this actually starts a Jupyter notebook, and I had launched one here already, so I'm going to go to this tab. So here you see this is how the tool comes up. You see sort of a depiction of a superlattice or a periodic potential, and this might be, you might be quite familiar with this, of course. And this is a model from the 1930s, 1932 or so, and you can calculate this analytically, and you have to use some graphing in order to get these eigenstates. And you can see sort of a very flat band here at the bottom of these quantum wells. You see the symmetry of the ground state band that has a peak in the quantum well. The next excited state would have a typical double peak in the wave function, and they decay in the barrier. And they're tightly bound, and the dispersion is very narrow, so the effective mass is pretty heavy. And at least when I was a student, I wasn't quite aware that really the conducting bands that really have a significant dispersion are typically actually above the barriers. And you see, actually then the peak of the wave function is above the barrier rather than in the middle of the well. And you see the dispersion really forming here. Now, what's kind of cool is that you can go into this tool and look at a variety of features. So here's this composite image of wave functions and a periodic potential and the dispersion. Now, you might want to just look at the normal dispersion that you see in the textbook. So here's the reduced dispersion. And you can also look at it expanded out over multiple Brion zones that are then folded in. But I think what's more eye-opening is this representation here, the expanded dispersion versus a free electron. So here you have the free electron in gray, and you see how the finite bands are beginning to sort of hug for higher energies, these free electron bands up here. And of course, you can pull out the energy functional that you see in textbooks that really define where the allowed bands are, etc. You can zoom in here and see these narrow energy bands of what used to be able to just you have to do this with graphing paper, right, to really get to these points and calculate the bands. So that's fine, that's dandy. Let's look at some other things. You can, for example, compare different potential types. So here's a triangular well. That's a nice concept where you can actually build superlattices today that might be triangular. I think what's really relevant is the Coulombic potential, which would be much, much harder to calculate analytically. And here you can see how the Coulombic confinement bands of a core atom would form a band structure here. And you can expand the energy range, etc. And then there's other potential models that are also interesting. But let's go back to the square. And let's say, well, we have this standard default input. What if we want to change some of the settings. What if we ask the students to compare what happens when you make these barriers taller? So let's just, for argument's sake, imagine we can make these barriers taller. What would we expect? Well, we would expect these wave functions to be stronger confined, possibly change the symmetry of the wave function. And I would expect that the dispersion here would change. It would become flatter because the electrons are more tightly bound. So let's increase this here from 3 eV to, say, 5 eV and see what happens to these bands. So I can go into the parameters here and change the maximum barrier height to, say, from 3 to 5. And let it go this way. And now I want to see the dispersion and the wave function. Now this is starting to run on NanoHub. This might take a minute or two because this is not a cached result. Maybe I should have run this before. So in some of these simulations, you can expect to wait like 40 seconds or so, especially in the new tool set. And as this is coming up, let me go back in here into the ABACUS tool set. So here is the more full-fledged version of the older style periodic potential lab. It sits in the framework that we call Rapture. So it's inside this gray box. It's not a web app like the other newer one, but you can basically get the same science and tweak a couple of parameters more than the other one. So here is the energy functional that I just showed. Here is the reduced dispersion like this. And you can go in and change the energy details. If I make now the barrier height, say, 4 eV, and simulate. The advantage, this tool runs a little faster because it doesn't have to connect to the web server that runs these this newer simulation. So here, let me go back, and I changed the barrier height, but maybe not enough. Should have increased it higher. So what you do see is that now the third state is confined more in the well. And indeed, you see a ground state, double peaked, and triple peaked. So you no longer have the peak in the above the barrier. And I can compare these things. I can click the compare button. Ooh, I should have cleared out. I'm sorry, I should have cleared out the Coulombic potential. Let me do that again. So now, let me see if I get the reduced dispersion with effective mass. Here we are extracting effective masses. You can see there's slopes we're attaching. This is what I wanted to show you. So here now these bands are flatter, but I made a mistake. I erased this older result. So let me go back in here and change it. So I'm sorry, I should have erased the Coulombic piece. So now here is the lower barrier of 3. That's the original result. And here I'm turning on the comparison. Gets a little messy, but you can see that indeed the third band here gets much flatter, and you see it really in this dispersion here, where I compare the two. So here is the 3 volt barrier, and here's the 5 volt barrier, and you can see how much flatter these bands get. So you can have students play with different dispersions and ask what if questions. What happens if I make barriers wider, taller, or make the well thicker, separate quasi the electrons from each other. So this is a standard model that's in every textbook, but there's a more graphical version to this where people can play and explore different dispersions. Now, this is a standard model, and when I took this as a student some 30 years ago, number one, I didn't have these cool animations. Number two, I can do all the math with periodic boundary conditions, but I had a hard time wrapping my head around this. So what I came up with is a slightly different way of explaining band structure. And that's what I like to share with you here. I'm going to show you this tool here that's in the list here. It's also in the main list here, transmission tunneling and band structure. So this is really an on-take on my favorite device, which is a resonant tunneling diode, where you can have two barriers like this, and you can calculate transmissions, etc. But for the purpose of what I want to show you today, I switch it to an N potential model. So I have N barriers. I'm going to start with two barriers like this. I'm going to run this and show you a double barrier structure with the transmission coefficient and the position of these resonances. So this is actually something I can have my students calculate analytically in my grad class, where they can calculate plane wave injection through a double barrier structure and calculate transmission. And it's good for them to know that there can be transmission through barriers, and that there are resonances where you can hit perfect transmission. And at that resonance, you get a certain eigenenergy of the system. Now, if I go back and make the four barriers, two barriers four, I have four barriers, three wells. What you should see is the formation of bonding and anti-bonding states here in the quantum well, and your transmission splits into three levels. So now here's a transmission with three peaks, and here are the positions of these peaks. And you can probably know where I'm going with this. If I now make this 8 and change nothing else, I'll get the transmission through these eight barriers, 7 wells, and I see 7 peaks, 7 eigenstates, and you can naturally see band structure emerging. And I find this model way more intuitive. My students seem to find that also more intuitive. You can I get sometimes questions, how many atoms does it take for band structure to emerge when you have a FinFET that's only 10, 50 atoms wide? Is band structure something meaningful? So those are then rather practical approaches to nanoelectronics, where band structure is really emerging in finite systems rather than these quasi-infinite periodic systems. And so you can look at all kinds of effects in these structures. And just FYI here on this, if I go back to the ABACUS page here, and I look at these band models. So these are actually, for example, animations that are just stringing together what I just showed. And it's also what I sent in, I guess, in the advertisement here. So you see, it's a slightly earlier version of the tool, but here is the animation of basically what I just showed you. Instead of having it all in one composite images, I had to string together many images some 10 years ago. So that's so we have some animations that you can carry in the classroom, where maybe you can demo it just like that. Animations in general are somewhat difficult to generate. It takes me about a day to do something to get the right images together, but then you have a product that really transfers well. Homework assignments. So there's a good apropos here. If I go back to the ABACUS homepage, there is a page here that's linked where we're trying to limit this to faculty only, because ultimately we also would like to include homework solutions, etc. So here is a page that is geared towards faculty members. And let me make this smaller again. So we have materials here, homework and project assignments. So for each of these tools, we assembled the various homework assignments that we have that go with these various tools. So my hope is that we assemble more and maybe streamline them more, and then ultimately also associate homework solutions with these such that you can introduce them into your classroom easier and grade them more easily. But at least some homework assignments are here. So here's something on the piecewise constant potential barrier tool that I just demoed, where you can have people students look at double barrier structures, reflections, etc. So maybe I can take some questions or in the question and answer forum. Hopefully that answered some items here. There are also some 3D band simulations. Yes. So that is here in Band Structure Lab. Let me pull it up in here. So here's this ABACUS tool set, and you can go to Band Structure Lab. And what that will do is launch a tool that is based on empirical tight binding. And you can look at a variety of things in 3D bulk. You can look at electronic band structure as well as phonon band structure. So we'll just talk about electrons and maybe look at silicon. And so here's your unit cell. Let's just include spin orbit coupling. So we have proper valence bands. These are some detailed parameters of how you want to march through the Brion zone. Let's just skip to simulate, and this will pull up the full band structure of 20 bands for silicon. So if I now, I'm going to have to modify this tool again. There used to be just a plot for the central band. So if I look at around the Fermi level, the zero energy level, so here are is my silicon band structure. So here is the minimum point on the delta line, and here are the 3 valence band with a split off band, etc. So let me zoom out again. Oh, by the way, I didn't demo that. In any of these tools here, you can click on this download button if you want your students to pull the data out. They can get the comma separated values, or if it's a plot like this, where you might want to get just the figure itself. So here's again my central bands. You can get an image in various qualities like IEEE journal format. You can modify your axes, etc., and then pull that out and download it. So you can get to these results pretty easily. But what I did have my students do last semester that is just ending, since strain plays a significant role in modern devices, I have them play with a variety of different strains. So if I, for example, look at strain this way, I can sweep the strain and maybe have it from hydrostatic from minus 0.5% of minus 5% to plus 5%. Of course, hydrostatic is on how to expand it out is not experimentally so relevant, but it's for teaching quite interesting. So I hit simulate, and what it'll do is it'll calculate these 9 different band structures under different strain conditions. I can zoom in here again, and I can see the band structure evolving for different strain conditions. So yes, we can do 3D band structure like this. There is a way to also plot the cylinders, but that cylinders, cigars or ellipsoid, but that takes quite a while to compute. You can do it. So what I'm asking my students to do in my class is actually to plot these trends of these different band edges and have them track the effective masses and see what that might do in bulk. And then I give them a nanowire design project where they can actually look at more interesting things that are really relevant today, where I have them design a nanowire for certain features, where they can look at really modified band structure in nanowires. It'll take a minute to run, or it actually runs it. So that gives you an idea. Yes, we can do 3D bulk, and then we can do band structure in nanowires as well. I see a question here. Do these tools connect to transmission formality for transport in quantum nanostructures? Yes. So this tool that I showed here, this guy, so what I do in my class, for example, I have the students calculate transmission over one barrier or through one barrier. I can put it here. I put in one barrier. And you can basically see that there is a finite transmission even below the barrier height that goes along exactly with the wave function formalism that Suprio teaches with plane wave injection. It's also part in any standard quantum textbook. And then analytically, you can, with a little bit of analytical push-ups, you can get expressions for transmission through double barrier structures, and then triple barriers, etc. Gets a little bit analytically dicey. You can do it. So then you do numerical. So yes, that fits right in.
Is there an easy way to directly measure or display the band gaps?
Yes. So this tool here, so I just ran the let me go in here and show you a bulk band structure. So here, even for the nanowire, it allows you to extract effective masses in this in the nanowire structure, and I'm going to show you that it can be done in bulk too. So if I go into just the simple bulk band structure, it does extract band gaps and effective masses. So here are the masses, and here are the band edge minima at the X point, at the L point, and the various masses in different directions as you would need them. So here in the conduction band, heavy holes, light hole, and the split up bands. I hope that makes sense. So you can, so indeed you can have students extract this information and then plot, say, the movement of this energy here in the X point.
Okay, I think our next question may be related. Does the tool for band structure account for effects such as band gap narrowing?
Not really. So, so band gap narrowing is a quite complex process. I think of it as heavy doping, and you get band gap narrowing. So that is not really included in this bulk band structure lab as such. So that's not in there. With NEMO type simulations, you can get to it, but that is not what's in the app-like tool here. I see another one. Can you also do 2D strain, like a layer of material with match? Yes. So let me clear this. So the question is, can you also do 2D strain, like a layer of materials with mismatched lattice parameters? So if you go into, for example, an ultra-thin body device that looks like this, and you can have a confinement direction, so that would be the vertical direction here, and a transport direction, say along here. It will allow you to, so it needs to have dangling bonds. It'll allow you to apply strains in the system as well. So you can apply a biaxial strain, for example, to the system and calculate it. So let me turn this off just so it runs a little faster, because it probably has it stored, I hope. It'll give you the 2D dispersion in this ultra-thin body, and you can squeeze it to get dispersions, etc. So yes, you can do it, and you can monitor how these band edges move up and down as a function of strain. And you can pull out, again, different masses from the different bands. And here's a visualization of the unit cell structure. So just a slab that is infinitely periodic. The structure of a nanowire is a little bit more interesting, because here we really see the round nanowire that goes into the 100 crystal direction, and you can compare dispersions in say 111 crystal direction to each other. And you can do the same here also for these different ultra-thin bodies, and have the wafer align in different crystal directions. But that should be the answer.
All right, our next question, is it possible to integrate the output of one tool to the input of another? For example, to integrate the output current of an RTD to a diode?
Not totally streamlined. You can export the data. We're working on driving these tools from Jupyter notebooks, where you can write your scripts that call these different tools and string the results together. I don't think that's ready for prime time, where I can demo this and see how the tools are strung together. But you can export the data. For example, here, if you go to the RTD negative tool, you can calculate meaningful IV curves for RTDs. So here's my best friend, resonant tunneling diode, that I spent early parts of my career at Texas Instruments. And it'll run an IV characteristic, and you can export the data through this download button. But and then you could string that into some other model. But it would be manual right now. And as I said, we're working on stringing this together through Jupyter notebooks, where I could call this tool through a Jupyter notebook. In many ways, that is one example here. The Kronig-Penney model is actually calling this older style Rapture-based tool and getting the results and representing them graphically nicer. It could pipe it into yet another tool in principle. So actually, this here is a Jupyter notebook, a sophisticated one. So we're working on that, but the general capability is not ready for prime time.
All right, we have another question. Can different crystal directions be used with the KP model?
I don't think I have a KP model enabled in this band structure lab. But so let me demo to you. Here is the nanowire that I simulated here in the 100 crystal direction. Okay, so let me simulate this in the 111 crystal direction. Oh. And run this. The unit cell number one will look different because the confinement is different, the transport direction is different, and actually the dispersion of such a nanowire will be quite different as well, and the effective masses will be quite different. This runs a little slower because now the 111 unit cell is actually twice as big as the 100 unit cell. So it runs a factor of 4 slower, but it should have the result here in a few seconds. So here you see a dispersion that is in the 111 crystal direction. You actually have the minimal point out on the delta line versus here the minimal point at the gamma point, and there's a minimum here towards delta, but it's much higher in energy. And you look at the structure, this is what I just showed you. Here you can see the 100 crystal direction. If I go in here, you can see that this is a 111 crystal direction. And you can also see that the unit cell, this periodic cell, has gotten twice as big to be really a repeated cell. And so, yes, you can look at nanowire transport and dispersions into different crystal directions.
All right, the next question is, what materials other than silicon is this tool set up to calculate?
Yeah, so let me see. It's sort of the standard ones: silicon, germanium, gallium arsenide, indium arsenide, ABACUS, and VCA-based silicon germanium. In principle, NeMo can handle a whole lot more, but we haven't coded that into this app here. So those would be the standard ones. So you can look at germanium, certainly in bulk, and germanium wires, gallium arsenide wires or gallium arsenide bulk, etc. And the ABACUS is, I believe, I haven't run this ABACUS for a while. It should be running within a virtual crystal approximation. And you can sort of set the aluminum concentration to, say, 30%. It'll assemble a tight binding band structure for that and calculate the nanowire. So those are the materials we have. Can we import other crystal structures with reconstructions of vacuum space for surface effects? Not in this tool. This tool here does not afford you to read in a physical structure. NeMo does, but this tool as an app does not. And by the way, these nanowires are passivated with hydrogen in order to avoid surface effects, surface states. Well, let me ask around, does this, which tool do you like better, the periodic potential lab, this kind of tool? Or do you think you can actually utilize this kind of tool as well, or with an animation? I'm just curious what you think. I think they're complementary. Yeah, there's you can, I mean, at some point I had a student actually overlap these dots with a periodic potential lab to convince them that they're really complementary models. They will give you exactly the same result, give or take some numerical accuracy issues. All right. If there's no other questions, we can also end the day early. This is sort of what I wanted to show. I can certainly always show more. Oh, I started my favorite resonant tunneling diode as a where you can export data. So here's an RTD, reasonably realistically doped. There's a central resonance. There's a transmission through the central resonance. And in this composite image, you can apply a voltage now, and current will rise as electrons are now flowing from left to right. And there's 3 plots overlaid here. Blue is a standard transmission, like here. But as soon as you have a bias, there's also then a current flow that is green, which is transmission times Fermi level right minus Fermi level left minus Fermi level right. And the light green one is actually the integral of the current. So you see that electrons are flowing through the ground state and electrons are flowing, and current rises roughly until the central resonance starts to hit the top of this well. And then eventually you increase bias further and you really don't have a supply function for electrons here anymore. And current drops, and most of the current now flows through the second resonance up here, and that's what the step function indicates. So this green guy here is really the integral current, and it indicates where the current is flowing. So there's a little bit of current still flowing through the ground state, but really most of it is flowing thermally excited, and then of course the rest up here is all thermally excited. So you can, if you wanted to export this current voltage characteristic here, you can do that and string it into another tool if you want. So if you want to get the raw data, it'll pop up another window, and you can save this data as a CSV file with some header in it. And you can string that into the next tool. And as I mentioned, once we're making progress on stringing these tools together with Rapture, you can pipe these tools together in a workflow as well.
All right, great. I think we've answered all the questions. Thank you everyone for joining us, and we hope to see you at the next session in the new year.
All right, yeah, thank you everyone. Have a happy holiday season. Be safe, and I'll see you in January. So thank you.